Okay, in the first two videos for Lesson 8, we talked about the binomial probability model and the geometric and Poisson probability models and how to use either the manual formulas or more commonly the calculator formulas to calculate various probabilities involving them. In this last video, we're going to talk about the distributions of these probability models, and we're going to focus specifically on the binomial and geometric models because they're the ones that are most frequently encountered in AP statistics. And we're also going to talk about a concept called expected value. So in the lesson on the discrete binomial probability model, we found the probabilities of all possible outcomes if we flip a fair coin 10 times using the binomial PDF calculator function, and we can see that these probabilities vary. They seem to be highest somewhere in the middle, and they get lower as we get towards the 0 and the 10 value. Right, so we can use a calculator trick to quickly visualize how that probability is distributed across these possible values. Let me walk you through the procedure. It's kind of neat. It looks like this. First of all, we would want to clear out our lists because we're going to use the list. So a quick way to do that would be to say second, then the plus key to get the memory menu, and then scroll down to number 4, clear all lists, and hit enter. That will clear out the lists. And then what we're going to do is go to statistics menu and click edit, so that we can edit the lists. And in list 1, we're going to put all the possible values of this scenario where we're going to flip a coin 10 times. So, and we're curious about calculating probabilities of numbers of heads. So we could have 0 heads, or 1 head, 2, 3, 4, and so we'll enter all the numbers from 0 to 10 here in list 1. So if you'd like to do this with me in your calculator so you can see how this works, just go ahead and enter the values 0 through 10 in list 1. Okay, in list 2, what we're going to do is we're going to find the corresponding binomial PDF value probabilities, but we're not going to calculate them by hand. We're going to let the calculator do that in a single step. So what we'll do is we'll go up here and highlight the name of the list, list 2, and we can enter an algebraic expression here for calculating what to do there. So what we're going to do is with the L2 highlighted, we're going to say second variables to get to the distribution member. We'll scroll down to binomial PDF, and then we'll say, okay, we have 10 trials because we're flipping a coin 10 times. Probability of heads is 50%, so we'll put 0.5. But for the x value, we're going to have the calculator get the value from list 1. So we'll put list 1. And see how it says L1 in colored letters there? We're going to push second and then 1 to fill in L1. Then we'll hit paste. You could do this with commas separated if you don't have this entry screen. And then with that on the command line, we'll hit enter. What that will do is that the calculator will go ahead and automatically compute all the binomial PDFs for 0, for 1, for 2, and fill them into list 2. Okay, so we put the matching probabilities in list 2. Then what we're going to do is we're going to make a scatter plot that displays list 1 as the x's and list 2 as the probability values. So let me walk you through how to do that. We'll say second mode to quit out back to the command line, and then we're going to go to y equals and make sure that nothing is in there. So if there's any formulas in there, clear those out. And then go back to second and then y equals to get to the statistics plots menu. Okay, with number 1 highlighted, we're going to hit enter to go into the statistics plot setup menu, and then we'll click on and then scroll down, and we'll make sure that this first icon, the one that looks like dots, is highlighted. And then we'll scroll down here, and if it doesn't already say so, we'll set X list to be list 1 by putting second and then the 1 key and then hitting enter. And then the Y list will be found in list 2, so that'll be second and 2, and then hit enter. Remember, you're watching a video, so if you need to, you can always pause and go back and watch that again. Once that's all in there, then we're going to hit second and mode to quit again to the command line, and then the way to get it to plot a statistics plot is to say zoom and then 9, which is the zoom statistics plot. Now when you do that, you'll get a plot that looks like this. I've stretched it out so it aligns with my values here. Basically, the height of this represents the probability of each of these cases. Right? So this being close to 0 means the probability of having 0 heads is very low. Probability of having 1 is a little higher. Probability of 2 higher still. The maximum probability there is for 5 heads, right? So if I wanted to, I could manually, I just added these manual bars here to indicate the heights to make it easier to see. that the probability is distributed across these individual discrete values. We can have the values 0 heads, 1 heads, 2 heads, all the way up to 10, and each of these discrete individual values has a probability associated with it, and the probability for 5 is the highest. That makes sense, because if there's a 50% chance of getting heads if we flip a coin, then that means about half of the 10 flips, or about 5, should be heads. It's also pretty likely to get 4 or 6 or even 3 or 7, but it starts to get less and less likely that we would have only 2 or 1 or 0 heads, or we would have 8, 9, or 10 heads, because we're pretty far away from that probability theoretical value of 50%. Okay, so this forms what we call the probability distribution, the way the probability is distributed across the outcome values, and that's why we have this binomial PDF. PDF stands for probability distribution function, so it's the way to calculate the particular distribution at any of these individual discrete values. Okay, so there's some things that are interesting to notice. The probability is not uniform, but it is symmetrical, and as we mentioned, it's most likely to occur at 5 heads. So what happens if the coin isn't fair? What if we had a coin that was somehow weighted so that it only landed on heads 20% of the time on average? If we go through that same process again in the calculator, I could just go back to the stats menu, edit, and just clear this list 2 out. The way to do that is highlight the list 2, hit clear, and then enter. That clears out everything, and then go back up here and highlight it again, and then let's re-enter the probability statement, binomial PDF, but this time let's make it the probability of having a head only 20% because it's an unfair coin. We'll still have list 1 values being used for the X values. And then when we populate that, say second mode, and then the statistics menu plot is already set up, so we don't have to reset it up. We can just say zoom 9 again and get this distribution. So here's the likelihood if the coin isn't fair, where it only has heads 20% of the time. So now the bulge is kind of the most likely value is 20% of the 10, or 2, and then 1 and 3 are pretty likely, 0 and 4 are pretty likely, but 5, 6, 7, 8, 9, and 10 are very unlikely, because we're very far away from the typical value of 2. Right? If we had a coin that was 70% chance of getting heads, then this distribution would be most likely value would be at 7 of the 10 would be heads. Right? The most expected or typical value is 7 in this case, and the probabilities near 7 are the highest. Okay, so this most occurring value, which you could refer to as the typical value or the expected value, is a measure of what is called the central tendency of the distribution of probabilities. So there are actually 3 main measures of central tendency that we use for data sets or probability models. We could talk about the mean, we could talk about the median, or the mode. The mode is the most frequently occurring value. The mean is the arithmetic average of the distribution, and the median is the middle value of the distribution, and that's usually applicable only when we're talking about specific data values. Okay, so the median and the mode are more applicable when we're dealing with actual sets of data. For probability distributions, we tend to use the mean as the measure of the central tendency. So for a binomial distribution, there's actually a formula for computing the mean, right? And it's kind of like the lambda value that we talked about for Poisson, right? The symbol we're going to use for the mean, though, is mu. It actually looks like a U with a tail on it, but it really represents the lowercase m in the Greek alphabet. It's pronounced mu, and we use Greek letters when we're talking about means for populations or for models. We tend to use the x bar value, the x with a bar over it, when we're talking about a particular set of data, and that's called a statistic. This is referred to as a parameter. We'll talk about that more later when we talk about continuous distributions. But in this case, the mean of the distribution would be the expected value, and we're going to do the same thing as we did for lambda for Poisson. If we have 10 coin flips and say the probability of a coin flip is 70%, then we should expect typically about 7 of the flips to be heads, and therefore that would be the mean value. And that is why this distribution has a central tendency of 7. We can also define various measures of spread, which is also referred to as dispersion or variability, which represent how widely the values are distributed around that mean. Right, there's three main measures of spread also. One is called the standard deviation, which actually represents the average distance that data values are from the mean. We can talk about something called the interquartile range, which is abbreviated IQR. That's the difference between the third quartile and the first quartile, where the quartiles are, the first quartile is the 25th percentile value and the third quartile is the 75th percentile value. And we could talk about something called the range, which is just the difference between the max and the min values. So again, the range is rarely used because it only depends on two extreme values. And the IQR, the interquartile range, is used more often with data sets. But standard deviation is the one that's the most common measure that we use for models. So we're going to focus on that one here. And it turns out that there's a formula for computing the standard deviation of a binomial distribution as well. The letter we're going to use is a Greek letter again, and it's this letter, which is called sigma. That's the lowercase s, s for standard deviation in the Greek alphabet, and it's used to represent the standard deviation for populations and models. Usually we use an actual lowercase regular s if we're talking about a data set. So here, it turns out that sigma, the standard deviation, can be shown for binomial distribution to be the square root of n times p times q, where n is the total number of trials, p is the probability of success, and q is the probability of failure. So here, the n would be 10, the probability of success having a head would be 70%, and the probability of failure would be the other 30%. So the square root of 10 times 0.7 times 0.3 is 1.4491. And that means that these other variables out here, right, are an average of 1.4, taken as a whole, the data set, if you think of it as the different outcomes weighted by their probabilities, they are an average of 1.45 flips away from the mean value of 7 flips. Okay, so if you want to know more about where these formulas come from, NP and specifically the square root of NPQ, there's a derivation for that, and I've got that posted on my teaching website at this address. So if you want to, you can look up and read that PDF document. It actually does require the use of some of the ideas that are in the Lesson 9 videos, so you might want to watch those first, but you can figure out where these are derived from if you're curious. Okay, so just to kind of summarize the binomial situation, a binomial probability model's distribution depends upon the probability of success, the p-value. If the p-value is 0.5, then it's symmetrical and it's centered right here in the middle, right? And the mean would be 5, and the standard deviation in this case comes out to be square root of 10 times 0.5 times 0.5 is just 1.58. If the probability is low, then that means that the probability will be what we call skewed right, which means that it's asymmetrical and there's a tail that's moving off to the right. Right? The most likely value will be 2, 20% of 10. And the standard deviation we can calculate. It's a little lower than in the symmetrical case. If the probability value were high, the p-value was 0.7, then this would have a central tendency, a mean value of 0.7, and it would have a skewed left distribution where the tail is off to the left to lower value numbers. So the probability and the symmetry depends on the probability value, and that's what the distribution of a binomial model looks like. Okay, let's do the same thing for a geometric model. We could talk about the values, right? We don't have a 0 in that case because we're talking about the probability of when the first success is. So it has to occur either on the first trial or the second or third, and it continues for some large unending number. We could do the same thing in the calculator. We could go to, for example, stat here. I could edit. I'm going to remove the 0 case because that's not applicable. In the geometric case. I'm going to clear my list out, and then I'll go down here and say let's fill this with the distribution for a geometric PDF model, and let's say, for example, that we have 0.5 as the probability of success. Again, maybe we're talking about flipping coins, and we'll get the x value from the list one. If we populate that and then we looked at the distribution, we would see something that looks like this. And the distribution, the highest possibility is that the trial occurs on the first value. There's a 50% chance that we would get a success on the first trial, that we get a head, say, on the first time we flip the coin. And then to have 2, we have to fail the first time and then get, so there's a 50% chance of failing the first time and then a 50% chance of succeeding the second time, so that's lower. That probability is 0.2. And since every time we're multiplying by another 0.5, the probability gets lower and lower and lower. So this has the classic exponential decay shape, a geometric model. And it will always look like that, actually. If we were to look at the geometric distribution for different probability values, 0.5, 0.2, and 0.7, all of them have an exponential decay curve. The only thing is, the higher the p-value, the steeper the curve is. And the reason why is because we're multiplying by the failure probability over and over again. So high p-values mean low failure values, which means we're multiplying by a third, by 0.3, 0.3, whereas this one we're multiplying by 0.8, 0.8, 0.8, so it's decreasing less rapidly. It always starts with the maximum probability value occurring on the first trial and goes down from there. And there are formulas for finding the mean and standard deviation of a geometric distribution as well. It turns out that the formula for the mean is 1 over p, and the formula for the standard deviation is the square root of 1 minus p over p. And let's see, so the mean for 0.5 would be at 2, and we can calculate the standard deviations. What I notice is that, that as the p-value goes up, then there's more and more probability found in the first trial, so the mean value is getting lower and lower. As p-value goes up, the mean value decreases. And also, because more is contained in the first trial, the variability also decreases. So as the p-value increases, the standard deviation decreases. The mean formula kind of makes intuitive sense in the geometric case also. Let's say that we had some other situation, like we're finding the probability that a part is defective coming off of an assembly line, and let's say the probability of a defect is 5%. There's a 5% chance of a part being defective. Well, that means that 1 part in every 20 is defective. So if we think about how often we would have to wait to see the first defective part, it makes sense that it would be 20 times, right? We would have to wait on average 20 times to get 1 part that's defective. Well, 20 is just 1 over the 0.05 value. So it's just 1 over p. And so it's kind of intuitive as to why the expected value, the mean, would be 1 over p. I've not been able to figure out a way to kind of intuitively say why the standard deviation is that formula. We don't actually see that formula used very often, even in AP statistics, but the mean one is used. Okay, so just to summarize, right, we've said that there's a distribution for binomial models. They're symmetrical in the case of 0.5 and asymmetrical otherwise, and for geometric models which always look like exponential decay. And we can compute the mean and standard deviation using formulas. Okay, one more general thing we need to talk about for probability distributions is the mean of a general discrete probability model. Now, we talked about the mean for specifically binomial and geometric, but what if we just by hand calculated probability values and we could come up with some probability model? It just wasn't one of our standardized models. Could we still talk about what the mean is of that? Well, it turns out we can. That's referred to as computing the expected value. So let's actually take a specific example. I think it'll make it more sense if we talk about a specific example. Let's say we have 100 tickets in a raffle, and 1 ticket is the winning ticket, and it's going to be worth $50. You win $50 if you get that ticket. 2 tickets are runner-up tickets. Those are worth $5 each. All the other tickets are losing tickets, and in that case you win nothing. So what is the mean or expected value of the winnings if you play this raffle many times? So if we wanted to solve this problem, we first need to find the probability model, right? So we could define a random variable to mean the winnings in dollars. And there's really only 3 possible outcomes. We can win no dollars, we can win $5, or we can win $50. And we have specific probabilities for each of those, right? 97 out of 100 times we win nothing. 2 out of 100 times we win $5, and 1 out of 100 times we win $50, because that's the distribution of the tickets. So we have a complete probability model, and that means that we can find something called the expected value. So the expected value needs to be something like an average, but it needs to reflect the possibilities of the outcome. So it wouldn't be right for me to say, oh, the three values are 0, 5, and 50. So I'm just going to say, let's take the average, 0 plus 5 plus 50. I'll just add them up and divide by 3, because that makes the assumption that they're all equally likely. If I want to find the typical value, I have to weight each value by its probability. So the definition of what we call the expected value can be given by what we call the expected value formula. It's just we're going to take a sum of each data value but times its probability so that it's weighted by its probability. So the mean value, the expected value, would be 0 times the probability 97 out of 100 plus we're going to take the value 5 weighted by its probability multiplied by 2 out of 100 plus 50 times 1/100th, and that turns out to be 60 cents. And that means that if you were to play this raffle many times, then you can expect to win on average 60 cents per play. Now that doesn't mean you ever win 60 cents. It just means that on average, if you take your total winnings and divide it by the number of times you played, it would average out to 60 cents per play. That's the mean value of a general distribution, right? So this is the formula that we use when we have a general model rather than one of our standardized models. Okay, by the way, you can also use a calculator to quickly find this expected value if you have a probability model. Let me walk you through the process for that. So let's go back to the command line and we'll clear out our lists. Let's go ahead and clear our lists out again. Memory menu for clear lists. So I'm going to go Stat, Edit. So what I can do is I can put the possible values, the X values, in my list 1. In this case, I can win $0 or $5 or $50. Those are the only 3 discrete individual values that I can have for winnings. And what I'm going to do is in list 2, I'm going to put the corresponding probabilities. So I'm going to put 97 out of 100 in there. I'm going to put 2 out of 100, which is 0.02. I'll just enter it as a decimal directly. And then 50 is 1 out of 100, which is 1%, so 0.01. So if I put the data values in list 1 and the frequency values in list 2, I can use another calculator feature to find the mean of that distribution. So if you go to Stat, let me show you this, right? If you go to, we're going to run the one variable statistics function. So you go to Stat, you go over here to Calculations, and you select one variable stats. We have to tell it the list that contains the data, which is list 1. Typically, frequency lists will be blank, so we have to tell it that the frequencies or the probabilities are in list 2. And then when we click Calculate, the very first line there, X bar, gives us the mean value, and this value down here, standard deviation of x's, gives me the standard deviation, so I can get the mean and the standard deviation. That means the expected value of this probability would be 60 cents. So that's how we can find that in a calculator. Okay, just to summarize, we have discrete probability distributions. The binomial and geometric model distributions can be found using the calculator functions for each outcome, and there are formulas for directly computing the mean and standard deviation for the standardized models. The formula for finding the mean, which is called expected value, is to take each individual value times its probability and sum them up. Or you can enter them as list 1 and list 2, and then find the mean and standard deviation from one variable statistics. So if you go on to the examples, we'll work a number of examples that use the binomial and the geometric models as well as the probability distributions in the examples and practice video.